let's talk about sampling distributions, all right? Now, the sampling distribution of a statistic, such as a sample mean or a sample proportion, is the distribution of all values of the statistic when all possible samples of size n are taken from the sample population, or sorry, from the same population. The sampling distribution of a statistic is typically represented as a probability distribution in the format of a table, a probability histogram, or a formula. All right, that's the general definition. This definition is the definition of the sampling distribution of means. So we have the sampling distribution of a specific statistic here, the sampling distribution of means. Now, the sampling distribution of the mean is the distribution of the sample means with all the samples having the same sample size of n taken from the same population. So basically, what this means is the sampling distribution of means is what we get if we have a population, right? We have a population over here. And from this population, we're going to take samples. So we're going to take samples of size n. All right, so we have sample 1, sample 1, and we have sample 2 taken from this population, and these are all size n. Sample 2, and we continue in this fashion all the way till we have all the samples of size n that are possible from this population. All right, so we'll say sample, let's say there are m possible samples of size n that can be taken from this population. So we're taking m samples of all of size n. And then what we're going to do is we're going to calculate the mean for each one of these. So this one has its own sample mean, so we'll call that sample mean for sample 1. This one has a sample mean, we'll call that sample mean for sample 2, all the way down to this one has a sample mean, we'll call that the sample mean for sample m. Right? So we have all these sample means, and what we're going to do is we're going to make a probability distribution out of them. So we're going to have the random variable being x bar, and over here we're going to have the probability of that random variable, p of x, and here we're just going to have all the possible values for x bar, x2 bar 2, all the way down to x bar n, and over here we'll just have the probabilities of each one of those. Okay, so that's what a sampling distribution for means is. We take a population, we gather all the possible samples of size n, we find their means, and then we make a probability distribution from those means. All right, we can also have a sampling distribution for variances, and it works pretty much the same way. Um, in this case, a sampling distribution for variances, and as you can see, you can have them for proportions too, but the sampling distribution of variances works the same way. Our population, we have our population of things, and we're going to draw different samples. We're going to call it sample 1, uh, sample 2, and the distinction is all these samples have the same size. They're all samples of size n, and we're going to take it all the way down to sample m. And then instead of calculating the means for these samples, we're going to calculate actually their variances, s squared. So we're calculating the variances for these samples, and once we've calculated all the variances, we're going to create a probability distribution based on these sample variances. So the random variable here is going to be sigma squared, and this would be the first, the not sigma, s squared. This would be s squared from the first sample, s squared from the second sample, and s squared from the mth sample. So we have s squared from all of these samples, all the way down to s squared from the mth sample, and then we find the probability of getting those particular, just like we found up here, the probability of get, actually, this is the probability of each x bar. Down here, we're finding the probability of each s squared value. So the probability of each s squared value would go here, and those probabilities would form this probability distribution for the sample variance. And of course, the last thing here is the sampling distribution for the sample proportion. And we do the exact same thing, except instead of calculating the sample variances, we would calculate the sample proportion, and then we'd make a probability distribution out of that. So the sampling distribution of proportions is doing the exact same thing we just symbolize for proportions instead of means or variances. Okay, so this is the notation that we're going to use for proportions. When we're talking about the population proportion, we're going to call that p hat. And when we talk about the when we talk about the population proportion, we're just going to call that p. But when we talk about the sample proportion, we're going to put this little symbol over the p, and we're going to call that p hat. So we're going to call this symbol p hat. All right, so now we have a couple weird symbols. Remember, we call this one x bar. And now we have also a p hat. All right. Now this is what happens when we take results from from 10,000 trials. All right. So basically, we have we have the population, and we're taking samples from this population, and we're rolling a die 5 times. So these are samples of size 5. N is equal to 5. The population mean is equal to 3.5. So you see here mu is equal to 3.5, but we're taking samples of size 5 from this population, and then we're recording the means of those samples. So all of those samples have different means, and we're looking at every single possible sample. So over here, we're going to have all the list of all our possible samples, and then we do the probability distribution and make a histogram for it. So this is the histogram for the frequency or probability distribution of the means. And as you can see, this distribution is approximately normal. We have approximately here a bell-shaped distribution. So it turns out that for the sample means, the sampling distribution for the sample means is always going to be approximately normal. The sampling distribution for the sample variances is skewed, however. So this is actually skewed to the right, as you can see here. And the sampling distribution for sample proportions is also approximately normal, approximately bell-shaped. So that's going to be something that we're going to use when we talk about the central limit theorem. All right, and the central limit theorem says, well, let's take a look at the theorem. We have some given information. So these are the criteria that have to be met in order for you to apply the central limits theorem. So the first criteria is the random variable x has a distribution which may or may not be normal, with mean of mu and standard deviation of sigma. So we have a random variable x that has a distribution that may or may not be normal, but we know the mean of that distribution, and we also know the standard deviation. We know the population mean and the population standard deviation, or we don't necessarily even have to know them, but they have to exist. And the second criteria is simple random samples, all of size n. So we have samples of size n being taken. Just like with our sampling distribution, we have a bunch of samples, all of size n, are selected from the population. These samples are selected so that all possible samples of size n have the same chance of being selected. Okay, these are the conclusions now that we draw from the central limit theorem. The conclusions are the distributions of the sample means will, as sample size increases, so as n gets larger, approach a normal distribution. That's what we were looking at up here. As n increases, well, this is not that large of an n, but as n gets larger and larger, this thing will look more and more like a normal distribution. So that's the first conclusion. As the sample size increases, the sampling distribution becomes more and more normal. Number two, the mean of all sample means is the population mean. So what that means is that the mean of the x bars, so the population mean of all sample means is equal to the population mean, which is kind of weird. That wasn't a guarantee. And number three, the standard deviation of all sample means. So the standard deviation of all sample means, which we'll put as sigma of the x bar. So this is the standard deviation of the sample means. Remember, we have now a distribution of the sample means, and that distribution has a mean and a standard deviation of its own. The standard deviation of the standards of the sample means is equal to the population standard deviation over the square root of the sample sizes. All right, and practical and common uses. Okay, practical rules commonly used. Practical rules commonly used. If the original population is not normally distributed, here is the common guideline. So the common guideline is that even if the original population is not normally distributed, for sample sizes larger than n, so if our sampling distribution has samples of size greater than 30, then the distribution of the sample means can be approximated reasonably well with a normal distribution. So even if the original data is not normally distributed, the sampling distribution, as long as the samples are of size greater than 30, will be approximately normally distributed. There are exceptions, such as populations with very non-normal distribution, requiring sample sizes larger than 30, but such exceptions are relatively rare. So the distribution of the sample means here gets closer and closer to the normal distribution as the sample size n, the size of all of those samples, increases. And the second rule that we commonly use is if the original population is normally distributed, then any size n, will be normally distributed. So it doesn't matter. If the original population is normally distributed, then all the sampling distributions will have distributions that are normal. All right, now here's some notation that we're going to use, and I just started showing it to you up there. When we see if all possible random samples of size n are selected from a population with mean of mu. So this is the population mean. This isn't the mean of the sampling distribution. This is the population mean, this mu, with no subscript. And standard deviation of sigma. This is, once again, for the population itself, not for the sampling distribution, because there's no subscript. The mean of the sample means is denoted mu of x bar. This is the mean of the sample mean. So this is the mean of the sampling distribution here. The mean of the sampling distribution, it turns out, is equal to the mean of the population. So the mean of the sampling means, the mean of the sampling distribution is the mean of the populations. And it turns out that the standard deviation of the sample means is equal to this standard deviation of the population divided by the square. All right, so this symbol, sigma x bar, is the standard error of mean. It's also called the standard error of the mean. So we have, this is the standard deviation of the sampling distribution, and it's also called the standard error of the mean. All right, now, this is what we're talking about here. Sampling distribution. So if we take samples of size 1 from a population that is already normally distributed, well, this is what the dot plot would look like. Now, if we instead take samples of size n and we calculate the sample means and we make a dot plot from those observations, then it will look like this, which looks really more normal here, right? More bell-shaped. This one is bell-shaped also, but it looks like the standard deviation here is even smaller. You see that? Because remember that the standard deviation of the sample means is equal to the population standard deviation, which would be actually the standard deviation from here, divided by the square root of n. So as n gets larger, the standard deviation of the sampling mean gets smaller, and we have a less spread out normal distribution or bell curve. So you see this bell is wider than this bell where n is equal to 10, because we'd be dividing by the square root of 10 to get the standard deviation of the sampling means. And this one, the standard deviation would be even smaller. You see, this is even a higher bell. So it's still a bell shape, it's just skinnier. Now here we have one where the original population is uniform. So the original population here is not normally distributed. But as you can see, if we increase the samples of size 10, it becomes a little bit more normal. And if we include samples of size 50, it's much more normal and the standard deviation decreases again. And here we have a U-shaped distribution. This is almost the opposite of normally distributed, right? It's not a bell. There's two modes. It's inverted hump. But if we take samples of size 10, then the sampling distribution looks like this, which looks approximately normal. And if we take samples of size 50, the sampling distribution will look like this, which also looks approximately normal. So it doesn't matter where we take our samples from, what the population looks like, what the distribution of the population looks like. When we start looking at the sample mean, or when we start looking at the sampling distribution and increasing the size of the sample, it'll become more and more normal. All right, now here's how we're going to use the central limit theorem. If we have an individual value from a normally distributed population, then we're going to use the methods from section 6.3, which is to find the z-score and then find areas using that z-score. That's what we were doing in section 6.3. Now, if we have sample values instead, and we're working with a mean from some sample or group, then we want to look at the standard deviation as being the standard deviation of the sampling distribution. And in that case, the formula needs to be modified. Instead of x, like we use here, since we're dealing with a sampling distribution, the individual values are actually going to be mean, so we're going to use x bar. And instead of dividing by sigma like we did here, since we're dealing with a sampling distribution, once again, we're going to divide it by sigma over the square root of n. So what we're really doing here is we're using the formula, we're pretty much using the same formula from 6.3, except we're taking into consideration the fact that, first off, we have x bar, and secondly, the denominator should be the standard deviation of the x bars, or the standard deviation of the sampling distribution. So that's all we're really doing. We're replacing x with x bar, replacing sigma with the standard deviation of the sampling distribution. And here's an example. All right, so let's look at this example. Okay, so it says using the central limit theorem. In exercise 5 through 8, assume that SAT scores are normally distributed. So we already know that we have a normally distributed population with mean of 1518 and standard deviation of 325. This is from the college boards. For part A, if one SAT score is randomly selected, find the probability that it is greater than 1600. Well, in that case, since we're dealing with an individual value, we're dealing with here an individual value, right? And this says if you're dealing with an individual value, you want to, that comes from a normally distributed population, you want to use the methods of section 6.3, which means we're using this formula. So for part A here, we're just using z equals x, which is the given x value, minus mu, which is 1518, divided by sigma, which is 325. So that's going to be, the given value is 1600 minus 1518, and we're dividing that by 325. And we want to find the probability here. So let's see. We're going to find this z-score. And the z-score here, let's see, that's going to be 1600 minus 1518. And we're going to divide that answer by 325. So we get a z-score of 0.25. All right, so now what we're going to do is we're going to use our TI-83 to find what area corresponds to a z-score of 0.25. Now, what we're looking for is the probability of finding a z-score that is greater than. We want a value that is greater than 1600. So we need to actually find the area to the right of this z-score. So this z is actually my left z-score when I plug this into my normal CDF. So what I'm going to do is we're going to use the normal CDF, oops, get back our value. We're going to use, like we did before, normal CDF, and we're going to put in as our left z negative 0. Oops, that's not negative, that's positive. So we're going to have our left z is positive 0.25, this z-score right here, right? And since that's the left z-score, this is the one on the left, there is no upper bound. So the right z-score is going to be infinity, so we're going to put in E99. So this is what we're looking for. We're looking for the area to the left of that z-score. So we take out our TI-83 calculator, and we turn it on, clear our screen here. And what we're going for is second distributions. We want the normal CDF, which is number 2, and we're going to put in a left z-score of 0.25 and comma a right z-score of E, which is above the comma, 99, which is infinity. So we get here 0.401. So this probability for part A is 0.401. So the probability of getting an IQ or of getting a SAT score X that is greater than or equal to 1600 is equal to, and we had that number here, 0.401. So that's equal to 0.401. And that is the answer for part A. All right, let's take a look at part B. Part B says if 64 SAT scores are randomly selected, find the probability that they have a mean greater than 1600. So this is pretty much the same question, except now we're looking at a sample of size 64. So now we have a value for n. So we're not using that formula for a single value anymore, because now I have 64 values and they have a mean. And we want that mean to be greater than 1600. All right, so now we're going to use this formula, because this 1600 now is no longer a value of x. It's the mean of these 64 values, so it's an x bar. So we're going to plug in 1600 for x bar in this case. And we're going to use the square root of n as our 64 as n. So it's going to be the square root of 64 down there. Now, there's an easier way of calculating this formula. Let me show you. This is algebraically equivalent to this. X minus mu, x bar minus mu over sigma, which is exactly what we just found. We just found this to be 0.25, but we can actually multiply this by the square root of n. So in this case, what I'm saying is, what we can do for part B, where we have a sample size of n equals 64, we can take the calculation we just did, which was z equals 1600 minus 1518 divided by, what was that, 325 or 624? 325. 325. And instead of doing a completely different calculation, we can just multiply this by the square root of 64. So we can take the answer that we just got, which is 0.25, and just multiply it by the square root of 64, which is 8. So what we want is, we want z to be a quarter of 8, and a quarter of 8 is 2. So if we use this z-score now, instead of the original z-score, well, we can go ahead and we can actually find this area using the central limit theorem. So once again, we're going to do normal CDF, but this time, instead of using 0.25, we're actually going to use 0.25 times 8, which is 2, and we're going from 2 all the way up to E99 again. So let's see what we have here. Let's take out our trusty TI, and we turn this on. Let's see, let's turn it on here. Let's clear it out, and we're going to go to second. Once again, vars to get to the distributions. We're going to the normal CDF, and we're starting at 2, and then comma, that's the left z-score, and we're going to E99. So second E99, close, and we press enter, and we get that this is equal to, what was that? 0.023. So 0.023. 0.023. So it turns out that the probability that x bar is greater than or equal to 1600, the sample mean is equal to 0.023. So the probability that the sample mean with samples of size 64 is greater than or equal to 1600 is 0.023. So that's how we apply the central limit theorem.